So I'll recount my trajectory, why I became interested. So maybe that will also make you interested. I am basically quantum field theory. Okay, that's my specialization. But when I was told that quantum mechanics has algorithms which are the most powerful conceivable algorithms, which was not even known to physicists for decades, right? It's only in 1980, 81 that people realized you could actually use quantum mechanics to do computation. None of us thought of that. The idea is that the wave function should encode the information that we want to process, as opposed to the wave function being encoded by nature about the atom, about the molecules. We don't encode that. Nature gives us the wave function and we experiment with it. In this case, we design the wave function. And then algorithm here is completely counterintuitive. When you do normal C++ or MATLAB or whatever you prefer, you want to add two numbers, you say A plus B, C. Here it doesn't work like that. Here you have this algorithm and it is uncertain the outcome. But you design it so that when you measure the outcome, the solution is most likely. It's completely upside down. So the whole way you design the algorithm, I'll give you an example, is completely counterintuitive. You have to think in a different way. So this field, I think like 60% of the people in this field are theoretical physics PhDs. Okay, another 20% are physics graduates. A small number are now engineers. It should probably increase because it becomes more successful. But the entire thing now resides on physics. If physics can make a breakthrough, this technology would not take off. So I will briefly go through this. I like to structure my talk so that you know where I'm going. So here's what I plan to do. So I already talked about the background a bit to you. Sorry, pressing the wrong button. So here's the background. So the great Richard Feynman in 1981, in fact, he wrote a book called Physics of Computers, Lectures on Computation, around the 80s. And this Yuri Manin, as you can see from his name, is a Russian theoretical physicist. They are the originators of this idea of a quantum computer. In 1983, David Deutsch, I think he's in Oxford, he wrote an algorithm, a quantum algorithm, which was faster than any possible algorithm classically. So some of you may know all this, but those of you who don't, so I'm going through this slowly, okay, so that I can spark some interest in you. Here are the problems that we are facing today. There are many problems we don't even know about. Here are the problems, the whole space of problems. This is what we can do. We hope to extend the domain of solutions to a bigger range. Quantum simulations, quantum search, algebraic problems. In fact, if you go to the popular press, there's huge number of articles on quantum computers, but they never discuss the physics of it. They say it can do this, it can do that, they can do miracles, fine, but how is it doing it? So I want to explain it to you. How does it do it? What's the magic? And there's some magic in this. So what I'll do, I'll start very slowly. I could jump into some complicated algorithm, but that won't help. The reason being that the two algorithms which are really the exemplars, meaning the outstanding examples, Shor and Grover. Shor's algorithm factorizes large integers into its primes. The problem that, I have a book on this, so if you're interested, just read the book, okay? We do Shor's algorithm in great detail. And, these books are all available, free download. So if I'm more interested in royalty, just go and you can find this for free, okay? So Shor's algorithm requires a large amount of number theory, which you may not know. And you have to define what are called quantum Fourier transforms, which are different animals from what you normally see. So I thought, instead of spending all that effort on things which are not directly algorithmic, I will just do Grover. Okay, Grover is straight algorithm, no other theoretical input required. So just to give you a summary, Grover's algorithm is you have a database of n objects. It can be the phone numbers and names in a telephone book of 1 million people. And so you want to search one specific name. You can say, well, I already know how to do it. I have alphabetical listing. Yes, you have. But here I'll give you the phone number. I'll tell you, find the name. Then you're lost, right? Then you have to go through the entire list, compare the name with the number, and you have to take n steps. But this, I'll show you, Grover, he does it in square root of n. So for a million, a square root of n is only 1,000. The other algorithms you can look into, they're more and more complicated. I have them in my book, but no need to discuss it. Now, interestingly enough, the biggest bottleneck in creating a quantum computer is the stability of the qubits. The qubit is a basic bit, is computer science, the ingredient of a classical computer. Qubit is quantum mechanical generalization. The problem with the qubit is that it has to be in a superposed state. You break the superposition, it becomes a classical computer. The problem is if you have a quantum computer in this room, and if somebody goes on the highway, you've broken your superposition. It's so fragile, extremely fragile. So the problem is to get a clean qubit, there's a name for it, I won't tell you. We probably need 100 ordinary qubits to generate one error-free qubit. But that's become a big problem if you want to scale up the machine. So the problem here is both engineering, a robust qubit, and error-correcting cores. I'll tell you how the normal classical computer corrects error. They send the signal 3 times, and they take the average. Simple. So if you have 110, the added is average is 0, that's 0 is it. And that's 90% time is good enough. So error correction is a very simple procedure in a classical computer, but they do error correction. In quantum computer, that becomes formidable. Okay, so let me go on. So here's some, so I mean, I will assume you know most of this, so I'll just rush through this. So here is the basic degree of freedom. It couldn't be simpler, is 0, 1. Remember, quantum mechanics is the following: the degree of freedom, Hilbert space, and result of measurement. The 3 levels. The degree of freedom can never be observed, ever. Because what kind of theory is this? I can never observe it? No. In principle, you cannot. Hilbert space? Yeah, you can, but mod psi square. You can't see psi. You can't see Hilbert space. It's here, but it's outside space-time. That's where quantum mechanics happens, and that's the secret of a quantum computer. Now, the way you do the algorithm is the following. These are gates. The gates are the name given in quantum computing to unity transformation. All of the quantum algorithms are reversible. So if you go and look up classical circuits, as they call them, they're irreversible. Like 2 lines can go into 1 line, you can never reverse it. In quantum mechanics, you must apply unitary, which means reversible gates. So you have a series of reversible gates. So you start with the wave function, pure quantum mechanics, and you evolve this wave function to the final state. That's it. This is a quantum computer, no matter how complex it is. The U's contain the algorithm. Doesn't look like a normal algorithm. So I'll give you an example, how things get complicated. So even say if you want to represent in this language adding 2 numbers. So how do you do that? You have to represent the number with a state vector. So you take one number, and so if you have 4 plus 3, you may need 3 qubits. So let me take 2 qubits. 2 qubits says 2 times 2 is 4. The 4-dimensional vector, another number, 4-dimensional vector, you tensor product them is 16-dimensional vector. And then you need a 16 by 16 matrix which acts on this 16-dimensional vector to add, say, 2 plus 3. So even addition is entirely redone in the language of Hilbert space and operators. This is an operator which adds numbers. And in my book, I spent a lot of time on that because I thought if you can't add 2 numbers, you can never do computation. All computation is addition. There's nothing else. Every single thing in the end is addition, no matter how complicated it is. So even Feynman's book, I was inspired by him. The huge amount of time he spent on adding 2 numbers. Because you have to carry a sign, you carry this, you have to carry that, a lot of half adder, full adder. So, I don't want to belabor that. But just to alert you that A quantum computer is another way. I'm okay now? Is another way of looking at arithmetic, as basic as that. So here is a single qubit. Okay, this is the beginning of a quantum qubit from bit. But qubit is a state in Hilbert space. It's not the degree of freedom. The degree of freedom is hidden. It's here. Of course, you have to normalize it for probability. This space is called a block sphere. It's a two-dimensional sphere. And so the whole computation takes place on that sphere. So look at this. You have 2 to n degree of freedom. So you have tensor product of all of these guys, n-fold tensor product, so 0, 1, 0, 1, 0, 1. So how many possible states you have? You have 2 to the n, right? So for example, if I have, say, a quantum computer, say if you want to break the banking code, you need about 1,000,000 qubits. Okay, so we're not there yet, but it's not so far. But suppose I have a quantum computer with just say 200 qubits. Nice, so 2 to the power 200 is something like 10 to the power 100, or 100 plus plus plus. That's more than all the atoms in the universe. This machine is going to use memory, which is more than all the atoms in the universe. We have to ask, well, how is it doing it? Where is it? This is not in the universe? No. The computation is taking place outside space and time in Hilbert space. This is never emphasized in quantum mechanical books. I mean, I teach quantum mechanics always, and I shock my students. I tell them everything is happening outside space and time. And when you perform measurement on it, you actualize a particular entity, which you see. So all of you sitting here is a result of measurement. Nobody will be here if there's no measurement. It all evaporates to Hilbert space. So this computation actually brings Hilbert space right into the lab. You can see the computation, but you can never look at the process because it requires memory more than the atoms in the universe. That's how complex it is. That is why it is so powerful. It's not just another supercomputer and more circuits running and more currents. No, a completely different algorithm. So what we do is that, instead of you writing this cumbersome note, it's not cumbersome, but the standard notation in the literature is that you can map this. There's 2 to the n states, right? You can map them into a list of 2 to the n numbers, and you can write a summation. So this is the state of a quantum computer in binary bits. So let me do the simplest case for you, right? Because there's no point showing you a very complex algorithm that you don't know the basis of what am I doing? Why am I doing this? So this is Grover. I think he was working in Bell Labs. The simplest case is that you have a list. You have a list of 4 entries. So you have A number, B, C, D. So this is like a phone book. There's a name A and it has a number. So you have a list. You have 2 columns and you have 4 rows. Okay. So one column has the number. The second column has the name. So then you're given this number. You said, okay, I'm giving you this number. Find me the name. So you say, well, okay, what I'll do, I'll check every number. And Zaha sees the result. But you need for that 4 steps. The four entries in your database. So here's what you do in quantum computing. You say, okay, create a database, map this data into Hilbert space. Create the state vector, X, which has all the information. Then you have to introduce an auxiliary qubit. This is the genius of Grover. Auxiliary because this qubit will disappear. It's like a catalyst. You need it in the intermediate stage, but in the final result, it doesn't matter. So I introduce an auxiliary qubit. Then I label this. I say, okay, this number is given to me. I don't know the name. I will label it by some psi. Psi is the qubit I'm looking for. Now I have a function which marks the qubit. So if I apply f on the state x, is 1 only when the x is equal to the marked bit, otherwise it's 0. Very simple. So here is the fundamental operation for an algorithm. This occurs many times, not always, but many, many times. It occurs also for Shor's factorization. That's what you do is say, look, it's called conditional gate. Conditional gate means that I apply the unity transformation. It's called the oracle. So this will displace the auxiliary bit depending on the value of x. So let's look at what it does, okay? So let's prepare an initial state. Initial state, you tensor product this Hadamard matrix. It appears everywhere. It's a very interesting matrix. It's unitary, but the determinant is -1. So it's in a discrete part of SU2. So hang on here. So here I create the initial state, phi. So I tensor product this 2 times. I tensor product my state vectors. I get this combination of every state is equally likely. The coefficient is 1, 1, 1, 1, 1. And that's usually the starting of all algorithms. You start with a state, but all of them are the same. And then you design your unity transformations, your gates, so that when you perform the measurement, you find the answer. So you don't know the answer, right? But your unitary gates will lead you to the answer. And I'll show you how it does it. So, okay, so here I have my auxiliary state. H1 is simply 1 is 1, right? So I act on H with 1, I get this state. Just notation, nothing else. So this is the state I'm looking at. So I apply my oracle. It's called oracle for some reason. I don't know, oracle. Apply oracle. You see, so here I have binary addition. Remember earlier was binary addition. This is binary addition. I forgot to mention that. This is binary addition, right? 0 plus 1 is 1, 1 plus 1 is 0 and all that, right? So here, so I 0 plus 1 and I 1 plus 1. So this becomes 1, this becomes 0. The minus sign comes out. So if you go back to the state that you're applying it on, this one has developed a minus sign for the state you're looking for. The rest of the qubits are unchanged. So now you realize that I don't need this. I'm just carrying it auxiliary. So I just define an operator U which marks the state. So you can say, well, okay, I've marked the state. Why can't I just observe it? The point, you can't observe it because the amplitude is going to be the same. It's just minus sign. Mod -1 square is 1. So you still, if you perform a measurement, so you can say, okay, I'll perform the measurement when I perform the oracle. But that oracle then has to be a measurement. It cannot be a unit transformation. It can't be a gate. You're measuring, you're collapsing the wave function. You don't know the answer. Where will you collapse it to? So you mark it with the transformation, then you need something else. You have to somehow amplify this. Just amplify this state so that when you perform the measurement, you will discover the answer. So that amplification is what the second step in the algorithm, amplification. So we have a gate W, apply this to the state. So Grover amplification is very, very interesting. Let me show you the graph instead of this, okay? What he does is the following. He says, look, here's my state before I mark it. I start with this state, the figure A. Then I marked it. I'm still not done, right? Measurement on this will give me nothing. Then he says, reflect each of the coefficients of the basis states about the average value of the amplitudes. So if you reflect this about half, it'll go to 0 because half is above half. But if you reflect this above the mean, this goes to 2. I've amplified it here to show you. If you reflect all the ones that you're not interested in, they go to 0 amplitude. And this one, which has come down, -1, he goes up and becomes 3/2 plus half, which is 2. So what you have done is that you have taken these coefficients, reflected it, amplified it, and said it effectively made all the coefficients 0 except the one that you are interested in. And that's the amplification that we are interested in. So of course you have to do it with a gate. So here's a matrix. This matrix acts on your state vector, which is now reflected. Notice the minus sign here. When you act on this state with W, you can verify it, you get the result. So this is it. All what I'll do later is the n-qubit generalization. So if you don't have this picture, it is a fog, why is he doing this? Why is he doing that? But with this picture, this is very interesting because with one application of the gate, I got the answer. Normally you have to recurse many times because if you have n qubits, it's not that simple. So let me do the case which is general. So just as in passing, you notice that the number of steps I took is square root of 4, which is 2. Again, a classical algorithm cannot find this in 2 steps. So general scheme is the following. You have now n qubits. You have to mark the state. Once you mark the state, you have to basically then apply the amplification. So here, just to go back to the idea of a phone book. So you basically have a phone book with a million names. Here's your database. You have a phone number and a name. So what the transformation will do, he will only look at the phone number in the database. And from there, he will mark it. So I prepare my state again. This is an n-fold tensor product because I have n qubits. So I have a lot of states here. Hyderabad matrix. I repeat the whole thing. I mark the state with this function, but now I have x has 2 to the n values. I do the transformation as before, but now it's more complex. So here I get the marked state. So here, notice what happened. When I apply the oracle, the marked state is only one of them. The rest are all equal to 1. One of them is -1. That's it. I don't know which one it is, but I know there is one, which is the state I'm looking for. So how do I do the amplification? So I've marked the state. The key to the whole quantum computer is that updating the state of the machine, the quantum computer. Simultaneously, I'm updating all possibilities. If you update, say, if you do a classical computer, you have to update each of the states one by one. And that's 2 to the n number of steps. And 2 to the n can be more than the number of atoms in the universe. So you have to do one by one by one. That's what the classical computer has a definite state. This state, a superposition, is a indeterminate state. Indeterminate doesn't have a value until you perform a measurement. It doesn't have a value. It is superposed. So what happens is that you essentially update every single possibility of the machine simultaneously. And that's the secret of the quantum computer. You can't do this on a classical computer. So I'm just repeating what I said. Basically, amplification, repeating the process, measurement, okay? So here I have to show you the math. How do I do this? So here's the math. I start with my oracle. Oh, I've dispensed with the auxiliary state. I don't need that. Then I notice that if I write this state vector in the language of the mark state, I have this expression. So that I rewrite my oracle in this language. Why do I do that? Because this will give me the amplifications. So by writing that, I have basically, now I'm in a position to define. The diffusion gate is the one which does the reflection. The diffusion gate is given by this. So now I look at the diffusion gate. So I have 2 steps, right? I apply the diffusion gate, which is a amplification, after I do the oracle. So you look at this is the oracle. This is the amplification. So here, if you look at the notation, the oracle acts on the state and marks the phi by decoupling it from the auxiliary state. So this U acts on the whole tensor product, but you rewrite it only in terms of O, and you have decoupled from the auxiliary state. Then you apply the amplification. It doesn't act on the auxiliary state. It acts on the mark state, the one which I have marked. So essentially, I get G. G is the rotation operator of Grover. That's what you need to study. So after all this algebra, you discover, well, what I need to know is what is G. How do I construct G? So G is the composition of marking the state and of amplifying it. Two things together. So I have drawn this for you because it's easier to just visualize it. So, okay, I need this. This is some vector eta here. Just note that there's a vector eta, right? There's a vector eta here. Phi is eta and xi is eta here. So here, what I do is the following. I have my initial state. Remember the whole point of the following. The initial state phi, I want to map it to my solution state, which is xi, the vertical axis. So what I do is that I take the n qubit, I find the vector about which I will reflect. I need that. Before that, I just added the coefficients. Here, I can't do that. It's much more complicated here. So I find the state vector, eta. I reflect phi about eta. After reflection, so how do I reflect? I apply the operator O on phi, and if you see phi and O phi, it's a reflection about eta. Then I apply the operator W to amplify O of phi to G phi. So the net result of marking and amplification is to rotate phi to G phi. That's why it's called rotation operator. Yeah, it's a composition of marking and amplification. So you can say, well, you still haven't done it, right? You're far from Xi. So how do you know you solved it? So what I'll show you is that if I repeatedly apply G, I will come closer and closer and closer to the solution. That's why I need many recursions. The example I gave of 4 qubits is very easy. But if you have, say, a million qubits, then you need all this technology. So here's the technology you need. So here, phi is decomposed into the solution state, the mark state, and this eta, which will be the vector about which I'll reflect. Remember, all these operations I'm carrying out in Hilbert space. Okay, there's nothing happening in the computer in real space. The computer is running, supplying the gates. It's evolving in time. It's not computer not sitting still, but the operations on the state vector are being carried out outside space and time. That's the key. You have to remember, and that's, ironically, most books don't want to say this. They say that Hilbert space is a mathematical construct, and hence is reality we don't care about. I mean, that goes back to Heisenberg, okay? I don't blame them. But when you look at the quantum computer and you ask, where is it doing the computation? It's doing in front of you. It's not in space-time. So you can say, what does this? I gave once an interview for some talk show from England, and they asked me, where is Hilbert space? How can anything be outside space-time? I said, don't ask me, go ask quantum mechanics. I don't know. I mean, this is what quantum mechanics is telling us, and I'm just stating it. I can say, no, it's a mathematical structure. But that doesn't answer the question, it's doing a real thing in front of you. So anyway, I'm very happy. In my book, I say it clearly. I say, I'm not going to beat around the bush. Tomorrow, quantum mechanics might be wrong. Fine. This is what it's saying today. So here is the crux of the matter. If you apply G many times, you recurse it, you bring it closer and closer and closer to the solution. So then you have this issue, how many times you have to recurse it? You must tell me, I've given you, 1 million qubits. I can't tell you, okay, you have recursed many times. What is many? So I have to give you a number. And so let me tell you how it works. This is the circuit diagram that is always drawn in the books. Circuit diagram means that here are the qubits coming in, and here are the auxiliary states. Here are the gates. As you apply the gates, and here's measurement. Remember, measurement is a non-unitary operation. It's irreversible. You can only apply it once. If you want to say, okay, I want to see what this is happening inside here, of course you can do it. You will collapse the algorithm. You get nothing. You can measure anytime. So someone said, well, I want to find out here. What happened here? Okay, perform the measurement. You'll get nothing because it hasn't recurred to the solution. You get it in the middle, and the moment you perform measurement, the algorithm stops. Finish. So you need to have a theoretical model. How long do I wait? When should I perform the measurement? It's entirely result of your algorithm. So here are some definition. Now this one, I have it's a long derivation. This algebra, you have to do it. There's no way out. So after applying the Grover rotation k times, this is the state vector that you have. Okay. That's a nice equation, actually. It's quite elegant. So you realize that what you want to do is you want to make eta's coefficient 0 as much as possible, and the coefficient of psi 1. Then you're done. Then you perform measurement, you'll find the answer. You don't know what the answer is, by the way. But you know from the algorithm, the performing the measurement, the most likely outcome is your solution. So if you want to be sure, you perform it 4 or 5 times. Always get the same answer, almost. So how do I fix the number of recursions? So then I say, okay, since I have n is large, so since n is large, theta is approximately 2 over square root of n. A simple expansion for trigonometry. So I have this expression for large n. So clearly, what I should do, 1 over root n is almost 0. So what I should do, I should make this term pi over 4, right? Because pi over 2 cosine is 0. Cosine pi over 2 is 0, sine pi over 2 is 1. Elementary, trigonometry. So I say, okay, I will choose the number of recursions to make this coefficient inside the cosine term pi over 2. That makes k equal to pi over 4 square root of n. So pi over 4 is a precise answer, but what you can say is that k is proportional to square root of n, which is what I started off with. I said the search algorithm takes square root of n steps, not n steps, to find the solution. So here we have it. After we recurse this many times, we are close to the answer. Perform the measurement. Remember, quantum mechanics, what measurement means is that I have these projection operators. I apply it on the state vector. So what it does is that it picks out one of the state vectors. And the probability of finding that state vector is given by the Morse square of the wave function. The wave function is not what you measure. You find the state vector. One element of Hilbert space you project into your lab. But the probability of choosing that state vector is Morse psi square. So you must remember that a measurement puts the wave function into an eigenstate. I mean, that's the formulation of measurement theory, right? You project it into an eigenstate of the projection operator. So you project it into the state X. Then you say, well, what is this state X? What's the likelihood? You say, okay, Schrodinger equation. Here I am. Morse psi square. Yes, I have it. This is my solution. I'm looking for this. So if you recount now, this is not your MATLAB or your C++ algorithm where you use common sense intuitive reasoning. Because when you write a code, you have written a code, it's very logical, right? I'll do this, I'll do the recursion, I'll call this, I'll do this. This is not the same. Every algorithm, you have to think from first principles. And, I like that because that gives physicists something to do. Okay, because this you cannot do without quantum mechanics. Okay, so we're quite happy physicists have a job. We have our solution. So now I'm done. I'll just summarize where we are now. So you can take this and go move with this. Grover's algorithm, I've shown that it's order square root of n. It's been shown that this is the most effective search algorithm that's possible. Yeah. Grover actually is an Indian scientist, although his name sounds like he's a Westerner, but he's not. He's an Indian scientist working in Bell Labs. Okay, so it is an incredible job he did. You'd be surprised to know the Grover's algorithm has been shown. Even electrons looking for defects do a Grover search. Even biology, they have Grover search going on inside the biological molecules. A lot of work has been done on this. So this Grover algorithm, nature knows about this. It's using it. The NP complete problems and the quantum counting, if you're interested in quantum cryptography, all sorts of things you can do with this. This quantum algorithm can be implemented by a simple circuit, the Hadamard gate, the oracle, and the diffusion operator. So those who are interested in computer science, they should compare this with the classical gates of a classical computer. Okay, so if you want to understand a quantum computer, you have to understand the classical computer. That's a must. So unless you understand the circuit and how the logic works, and you have Boolean algebra, you have all that, this and or nor, all that you have to know. Only then can you make a quantum gate. So that's the computer science of it, right? I mean, you have to do some computer science. And as a physicist, I'm happy to see that the one subject which is outside physics is chemistry, physics is biology, but information science seemed to be away. But with this is the grandfather of information science, quantum computing. Classical computers are the limit of this. It's a classical limit of this. So physics has now reached information theory as well, not only through black holes and information paradoxes, but in hardcore quantum computing in the lab as well. There's a limitation of Grover's algorithm, which is a quadratic speedup. If you really want to be impressed, go study Shor's algorithm. It's exponentially faster. And so that's, I mean, MIT gave an award to Shor recently because he showed that factorizing primes, which is a very practical issue for cryptography, can be cracked by the quantum computer. Of course, you can have quantum cryptography also, because if you use entangled states and all that, nobody can crack that. But that's another level of encoding. If you do a quantum entangled state, any measurement performed on it, you will know immediately. And so you can't crack that code. But here it is. If you really want to see an exponentially speeding up of algorithm, please look at Shor algorithm. Okay, I'm done. Thank you. Any questions?
Really great Apple and she asked question the way that that's I think we had some maths figures some fear it might it is being sick is in my get we'll see. So, uh, uh, what is of how many gigabytes one needs to apply to search out and include information? How many
Trace.
one should apply to search out any KB information?
So it depends on your interest, right? I mean, as I said, if you want to crack the banking code RS 0, either 2027, you need 1,000,000 qubits, okay? But if you are searching small things, like, IBM is claiming they will have 1,000,000 qubits in a few years. So the more vast the database is, the more qubits you need. One thing I should mention is that the most promising approach is hybrid computing, that you let the classical computer run and it hits a bottleneck. So this computer is most useful when you need many recursions. If you few recursions, supercomputer can do it. So you run the supercomputer, then you port it, you send this information to the quantum computer, and then it solves it for you. So that's been the most fruitful application so far. So to answer your question, say if you have an exponentially large database, then Grover is in trouble, right? He's only square root of n. So if you have an exponentially large, then okay, can't do much.
For 4K big system, how many gigabytes for this file?
That's a very good question. Okay, I think there's a term. These founders of quantum computers have have said made the benchmark. I think is 70 qubits. You need more atoms in the universe. So that's the sort of benchmark. They've said that for 70 qubits, the information that you need to store the processing is more than the atoms in the universe, and that's where classical computers are basically been left behind. So it's not that far. No, but I think 30, 40 qubits people have done all that. By the way, who was interested? There's something called Qiskit. Qiskit is a free access to a quantum computer. I think they give you 5 or 10 qubits. And, it's very friendly. You can program it by just looking at the icon and dragging it with your mouse. You don't have to write any code. And do some simple things. Just say, okay, 2 times 3 is what? Okay, 6. So he will do some computation for you, will produce a result. I strongly encourage you all to look at this. You know why? Because this is a new field. And this is a field where you can have an impact without studying supersymmetric, Yang-Mills and, 4 dimensions or 10 dimensions. Superstring theory is fantastic, but the amount of mathematics you need to reach that point is enormous. This is quantum mechanics, but algorithmic, not straightforward quantum mechanics. But I'm not a salesman, okay? You can do whatever you want. I just feel it's a good subject, Do whatever you think is of interest to you.
Yes, slightly off topic, but because you mentioned his cryptographic application, um, is there a problem of like quantum computing, like breaking symmetric cryptography? Like, is it the same level as like the Y2K bug, where like eventually we will have to come up with a gate basic?
Sure. Yeah, the question is, remember Y2K, there was a lot of effort to make sure that the codes don't break down. So people are already trying to make quantum computer resistant codes. So it's a question of how long will this take? And, in physics, things happen suddenly. It's not linear. Like some breakthrough will happen, you can suddenly make stable qubits. Then you can make 1,000 qubits. So the progress is not that far. So people are already trying to hedge their bets. But my only fear is that the first people to use this will be the military, unfortunately, and they will not reveal what they know. So that's out of our control, right?
Will it break things like RSA?
Definitely. RSS, this code, you need 1,000,000 qubits and about half an hour of quantum computing time. That's all, which is not that far away. Yeah. That's a huge, this like 2,000 long integer that you're factorizing is not a simple exercise.
I was thinking some of your favorites to tie it and it see, but I saw that apply what up and by having hats to you. Curious.
I have. So, I was discussing with Prof. Raju that, I discovered, and I say this with all reservations, I may be wrong, that forward interest rates, which many of you may not have heard of, is a 2-dimensional quantum field. So you may say, this is crackpot stuff, man. This is not true. So, of course, you have to verify the data. So data, supports my model to 95% accuracy. Then I applied quantum mechanics to the pricing of commodities with a Lagrangian Hamiltonian. Very complicated, right? These Lagrangians have x double dot square. See, in physics, a Lagrangian is x dot kinetic plus potential, right? All the Lagranges in finance are x double dot square plus x dot square. X double dot means both x and p are known because they're boundary conditions. And these are non-Hermitian Hamiltonians. So non-Hermitian Hamiltonian, entirely new field because only you see Hermitian Hamiltonians. Non-Hermitian Hamiltonian is another whole field. And that's, you have to master that to apply it to commodities. So that's an interesting field also. I've applied it to all sorts of things, okay? I don't want to even elaborate on that. But the main thing is quantum mechanics and physics is a fantastic subject. If you master physics, you can study anything you want. Seriously. So I'm happy to see so many of you here. I was afraid there'd be no audience. I said, physics may be a unpopular subject, but physics is really very, very useful. And theoretical physics, I found it is a tool that you can apply. I even have models of, human consciousness using quantum fields. And if you think this is really crackpot stuff, it's not. We have a book and experiments to show entanglement of consciousnesses and all that stuff. So there's no end to what you can do. There's no end to what you can do. It's up to your imagination. But remember, one thing, I always did this, you must anchor this on data. The moment you leave physics, you'll be called a crackpot, right? So if you have data backing you, then no one can question you. You have to have data. So I always have empirical tests, even till today. So it's very, so like I'm now into, mathematical Islamic finance, which sounds like another wild idea. But I'm using data for that. I was discussing with Prof. Raju, the Islamic finance is much more complicated than normal finance because all cash flows are stochastic and indeterminate. If you take a coupon bond, I don't know if you know what a coupon bond is. You take a bond is sold to you with coupons every 6 months, and then you get the principal back. Those coupons are fixed. But from the Islamic point of view, the coupons cannot be fixed because you must participate in risk to take any return. So the coupons being fixed means the interest rate. So then the coupons being stochastic means another level of complication on the underlying instrument. It's very complicated. So, if you don't do serious Islamic finance, you can just copy Wall Street, end of story. That's what most people are doing, by the way, unfortunately, okay? But if you're serious about it, you have to have new mathematics, which is also, my models are all based on physics, okay? So it's another physics model there, which combines stochastic coupons with risky instruments. It's a long story, I don't want to be, but it's all very interesting, okay? I'll leave it to you, young generation, to do what interests you. That's the most important thing.
Any issues? Any other question?
Why do we use the two system when we do quantum computing while a 3-level system or a 3-level system? Why not a 3-level qubit quantum state or a 4-level quantum state?
Why qubit? Why not a triplet? That's an interesting question. I mean, I'm sure we can do a 3-level state as replacing a qubit, but probably it's reducible to a two degree of freedom. The 2 degrees of freedom, if you have a degree of freedom with 3 values, not 2 values, right? The 2 values can probably two qubits can make this 3 qubits in some approximation or some simplification. This is the simplest, okay? That's all I can say. See, if you look at a classical computer, it's either off or on, 0, 1. That, okay, I'll give you a more theoretical answer. The binary expansion, 0, 1, 0, 1, 0, 1, can represent any number whatsoever. So any 3 state you give me will represent finally numbers, which finally can be translated into 0, 1s. Finally. So finally all be 0, 1s. I will not say no. You might be right. Maybe faster. I don't know. All I'm saying is that it'll be equivalent, but maybe more efficient. Yeah, that's possible. No one has explored that, by the way. At least I don't know.
I think everybody is characters now. So why don't we thank Professor Baaquie? Professor Baaquie will also speak tomorrow at the dinner.